Yeah, so thanks for inviting me to speak here today. As Manivata said, I'm at the University of New Hampshire, and I'm an N3AS member here, working mostly on numerical simulations of black hole neutron star and neutron star mergers using the numerical relativity code SPEC, which is developed by the SXS collaboration. In this presentation, I'd like to start with a discussion of some of the connections between neutron star mergers and nuclear physics and N3AS science, which for many of you will probably be a little bit of a review more than anything, but maybe not for everyone in the audience. And then after that, I want to focus more on what we have learned from numerical simulation about the dynamics of particularly black hole neutron star system and a little bit neutron star merger as well. But I'm focusing mostly on the black hole neutron star mergers here because we already had a very nice talk last semester by David Radice on the dynamics of neutron star mergers. And so I'm going to focus mostly on the other one here. So we're going to see what the outcome of each of these mergers is and what we have learned from numerical simulations about these systems. And then after that, I'd like to move to what the main limitations of simulations are at the moment and how that can impact our ability to extract physical information from observations of neutron star, and black hole neutron star mergers, in particular information about nuclear physics in these systems. All right, so before getting started, let me give you a more visual idea of what is happening in one of these systems. This is a black hole neutron star merger from one of our simulations from a few years ago. The black hole is initially on the right here, the neutron star on the left. And that mesh that you can see in the middle is the initial equatorial plane of the binary, which is mostly there for reference. It doesn't have a particular physical meaning. What is going to happen is that the neutron star is going to orbit around the black hole and in some cases at least eventually get tidally disrupted by the gravitational field of the black hole. And we end up with the ejection of maybe a few percent of a solar mass of very neutron-rich material. The formation of an accretion disk, a very hot, massive accretion disk that can contain maybe 10, 20, 30% of the mass of the sun. And then the rest of the neutron star, the vast majority of the neutron star, is rapidly accreted onto the black hole at the center of the system. And just to note the timescales here, the entire movie here lasts about 20 milliseconds. And the rapid accretion phase, where most of the neutron star is destructed and then accreted onto the black hole, lasts maybe 1 or 2 millisecond order of magnitude. So that's a very fast process. And then that accretion disk that remains after the merger is going to evolve for multiple seconds after the merger. And during that time, it is going to continue to eject matter in disk wind. And the ejection of material is one of the most important things that we are going to be interested in these systems, because this is where most of the electromagnetic emission coming from these systems is going to come from. Either mildly relativistic or ultra-relativistic outflows coming from the remnant. And also because in that neutron-rich material is where our process nucleosynthesis is going to happen. All right, so in terms of connection to nuclear physics in these systems, there are two particular connections that I'd like to make that will be important for the rest of this talk. The first is that, of course, we would like to use neutron star mergers to better understand the internal structure of neutron star and the composition and properties of the core of neutron stars, which are at this point are not very well constrained. And for any nuclear physics model that you might have for the internal properties of neutron star, for the properties of dense nuclear matter, you are going to be able to build an equation of state, so pressure and internal energy as a function of density, temperature, composition. And in particular, for any zero temperature equilibrium composition neutron star, you can build a mass radius relationship for neutron stars which is going to be a characteristic of cold neutron stars in equilibrium. And if we can actually measure the mass and radius of one neutron star, we can get some constraints on the equation of state and thus accordingly on the nuclear physics inside the star. So that's one way in which merger can help us, both black hole neutron star and neutron star merger, in trying to determine what the size of a given neutron star is. The second method that will be at our disposal to constrain this equation of state using mergers will be to take advantage of the fact that all of these equations of state have a maximum mass, beyond which you cannot support an isolated non-rotating neutron star. And so if you can actually constrain what that maximum mass is, either by directly measuring a star of a certain mass or through other means during mergers, as you will see, you can actually get additional constraints on the equation of state. So either measuring the radius and mass at the same time or measuring very massive star or the properties of the maximum mass of isolated neutron star is going to be helpful. And the second aspect of nuclear physics that we are going to try to understand with these neutron star merger is the production of heavy elements, specifically the elements produced through rapid neutron capture nucleosynthesis. We know that if we have neutron-rich material ejected in either a black hole neutron star or neutron star merger, or in one of those post-merger remnants, that neutron-rich material is going to undergo our process nucleosynthesis, forming a large fraction of the heavy elements. And we would like to understand how much merger contribute to our process nucleosynthesis and exactly what type of elements they produce. And it turns out that the outcome of nucleosynthesis is very dependent on the composition of the outflows produced in these mergers, and subdominantly in mergers on the temperature of these outflows. And so in order to actually predict how much merger contribute to nucleosynthesis and what kind of elements they are going to produce, we need to be able to predict for any given merger how much mass is ejected and what the composition of that ejecta is. So those are some of the most important predictions that we need to make. And then to actually know what the contribution to nucleosynthesis is in the universe, we need to combine that with actual population of merger events that can be constrained, hopefully from gravitational wave observations and possibly also from electromagnetic observations of these systems. So once we have an event rate for any given type of system and predictions from numerical simulations, for example, for the amount of matter ejected by any given system, we can try to predict how much these systems contribute to our process nucleosynthesis. Another way at which we can get in to this process is that the ashes of the R process are going to radioactively decay, and these decays are going to release energy in the ejecta, which a few days to a week after the merger are going to power a kilonova, optical infrared transient. And again, the magnitude of the kilonova, the duration, the color and color evolution of the kilonovae are all dependent on the mass of the outflows, their composition, as well here, their velocity and geometry are going to be important. And so the first thing is that because different mergers are going to produce different type of ejecta, we can try to use kilonovae to extract additional information about the properties of the merging objects. The masses of the merging objects, maybe the size of neutron star, which also influence the amount of mass ejected, and so on. But also because different outcome of the R process can have a significant impact on, for example, the color of kilonovae. We can actually hope to directly connect the observations of kilonovae to what was, at least some of what was happening during our process nucleosynthesis. So that's the kind of thing that we can hope to do. All right. So now I'm going to move to actually what we know about the dynamics of mergers from numerical simulations, starting with black hole neutron star system, which I'm mostly going to be focusing on here. So in a black hole neutron star system, we mostly have two potential outcomes, according to what simulations tell us. One is that the neutron star is disrupted by its black hole companion, as we have previously seen. And again, this is going to result in the ejection of neutron-rich material, a few percent of solar mass, and the formation of these disks. The other potential outcome is that the neutron star is going to orbit the black hole, but then it's going to reach the innermost stable circular orbit of the black hole without disrupting, at which point it is just going to plunge into the black hole, leaving no matter behind. So again, in the first case, you can have a kilonova. If you are interested in gamma ray burst, you can also potentially have a gamma ray burst. While in the second case, you probably have neither, or if you do, there's only a very small amount of matter left outside, and it's going to be a significantly weaker signal. So from relatively simple Newtonian or relativistic arguments, you can actually get a good idea of what the important parameters are going to be in determining the outcome of a black hole neutron star merger. And then from simulations, we can actually develop fitting formulae that tell us which systems exactly are going to disrupt and which ones are not. And if a system disrupts, how much matter is left outside after merger to power electromagnetic signals after the merger. And the three most important parameters are the mass ratio of the system, the compactness of neutron star, and the spin of black hole. The compactness of neutron star is probably the easiest to understand. If you have a large neutron star, which is more weakly bound gravitationally, it is going to be easier to disrupt it. And so large neutron star values or small compactness is going to be favorable for disruption. So typically, larger neutron stars are going to eject more matter. The mass ratio is a little bit more complex, but basically the more asymmetric the system is, so the more massive your black hole is practically, the harder it will be to disrupt the neutron star. If you are familiar with tidal disruption event, for example, you might also know that the same principle applies, that the main sequence star might be disrupted by a relatively low mass, intermediate to low mass supermassive black hole, while the more massive supermassive black holes are not going to disrupt a star. The same is true for neutron star, but with much less massive black holes. If you have a neutron star around 3 to 5 solar mass non-spinning black hole, you can disrupt the neutron star. But if you get to higher mass black holes, it's going to be very hard to disrupt it. This is particularly relevant if we consider the population of black holes currently observed by LIGO in binary black hole merger. In that most of those black holes are relatively heavy, above 10 solar mass, and relatively low spin, which we will see also matters. And that means that if the black holes in black hole neutron star systems are similar to the black holes that we observe in black hole systems, which is not guaranteed, but if that's the case, then it's going to be very hard to disrupt a neutron star in a black hole neutron star system. It's going to be a more common occurrence for a black hole neutron star system to lead to no disruption of the neutron star. And finally, the last parameter here is the spin of the black hole. And the more rapidly the spin, the black hole is spinning, especially the spin along the angular momentum of the binary, the easier it is to disrupt the neutron star, because you can get closer to the black hole before plunging into the black hole. Right. So that's a general idea, and then we can make actually quantitative prediction, for example, in that paper that we wrote a couple of years ago. So what can we actually do then when we have observations of black hole neutron stars? Well, the ideal case would be if we have one of these events where the neutron star is disrupting and we also observe it through gravitational waves, both gravitational waves and electromagnetic signals, because then we would be able to put pretty strong constraints on a combination of the radius of the neutron star and the spin of the black hole. Unfortunately, that's not where we are at the moment, because so far, well, first LIGO has not, LIGO and Virgo have not, with any certainty detected the black hole neutron star merger. And even the events that might be black hole neutron star mergers have not had any electromagnetic counterpart. The most interesting event, probably in terms of potential black hole neutron star merger, is GW 190426, which has some probability of being a terrestrial event, but still more likely than not to be a real gravitational wave event. And if it is probably a black hole neutron star system with mass ratio of 4 to 4. So relatively low mass black hole neutron star system. And before LIGO released the parameter estimation for this event, we actually used the fitting formula that I mentioned before to place an upper bound on the spin of the black hole, consistent with no observations of electromagnetic signals. Now, this is a weaker method than actually observing gravitational waves and electromagnetic signals for two reasons. One is that the constraints are going to be actually pretty weak because most black hole neutron star systems are going to naturally lead to no disruption and not much electromagnetic emission. And the second reason is that it is only valid within the region of the sky that was observed by electromagnetic observatories. On top of that, we have to take into account the fact that there could have been a weak kilonova that was not observed. And so it could have disrupted but not produced much ejecta that would still be compatible with the data. So we end up with the kind of constraints that we see here as a function of the mass ratio of the system. So mass of the black hole divided by mass of the neutron star. And the radius of the neutron star, you can put a maximum bound on the spin of the black hole. And you see that for compact star, it's basically no bound at all. The maximum value is 1, and we can barely constrain it to be less than 0.9. And for larger stars, you start putting some slightly more constraining values. So more recently, LIGO did come out with parameter estimation for this system. And it turns out that the most likely mass ratio is around the green line here, but there's a pretty large error bar on this that actually goes out of this plot. But more importantly, the maximum spin of a black hole allowed by the gravitational wave observations is below any of these upper bounds here. And so far, all we can say is that the gravitational wave parameter estimation are consistent with the constraints that we derive from the absence of electromagnetic signal, which is reassuring, but does not reach the point that we are really interested in reaching, which would be to actually get additional information from the electromagnetic signal on top of what we get from the gravitational waves. Hopefully that will be possible if we actually do observe joint gravitational wave and electromagnetic signals in the future. That's the kind of thing that we can do at least. All right. Now I'm going to talk very briefly about neutron star mergers. And again, I would redirect you to David Radich's very nice talk last semester for more details on the dynamics of these systems. The outcome of the merger here is going to mainly depend on the total mass of the system, the mass ratio, how asymmetric the system is, and again, the size of neutron stars. But maybe the most important point is whether the two neutron stars are going to rapidly collapse to a black hole or not, which is determined by the total mass of the binary and some threshold mass that is equation of state dependent. That actually depends on the maximum mass of neutron stars. And so if the neutron star system is very massive, the remnant cannot support itself against gravitational collapse, and we are going to rapidly form a black hole surrounded by a very low mass torus because most of the matter falls into the forming black hole. While if the neutron stars merger as a lower mass, you are going to have a neutron star surviving temporarily or permanently, and in that setup, you can actually form a more massive disk around the remnant and have more of a chance of producing outflows, GRBs, and kilonovae. So this is probably the most important determinant. Subdominantly, the asymmetry in the mass of the system can also lead to more mass ejection because the lower mass neutron star can be partially disrupted by its companion. But that requires pretty asymmetric neutron star mergers, more asymmetric than most neutron star mergers observed, for example, in the Milky Way. All right. So that's the kind of predictions that we already have at our disposal. We kind of know what the outcome of the merger is as a function of the initial parameters of the system, and we can predict how much mass is ejected, certainly in the black hole neutron star merger, how much mass is going to remain around the remnant. In the neutron star mergers, there are also predictions for the same quantities, also they typically come with somewhat larger error bars because the system is more complicated to model. But that's still the part of the problem that is fairly well understood at this point. Where we are really running into large uncertainties in our ability to model outflows and thus kilonovae is in the production of post-merger outflows. They are very important kilonova models because somewhere between 15% to 50% of the mass of the disk is going to be ejected if you have a black hole disk system after a merger. This has been shown consistently by a number of simulations. And on top of that, if you have a neutron star at the center of your remnants, you might go higher than 50%, 90% or more. So a very large fraction of the mass of the disk might be ejected. And that's in the neutron star merger, that's going to actually dominate over the matter ejected at the time of merger, while in the black hole neutron star merger, it might be comparable. And the main source of uncertainty in that number is not numerical uncertainties in the post-merger simulations, so much as what the large-scale structure of the magnetic field is after a merger. And we'll see in a minute why this is a problem for us. So that's one important source of uncertainty. Another one is that we do not have very good prediction for the composition of the outflows produced after a merger. And that is in large part because these post-merger simulations do not have detailed neutrino physics, at least most of them. And so most of the predictions we have for the outflows cannot reliably predict the composition of the outflows, which is crucial to understand our process nucleosynthesis and the color of Kidanovi. Let me talk briefly about those 2 points, and then talk a little bit about what happens after the matter is ejected. So let's start with magnetic field, and I'm going to use here a simulation by Sasha Chonglazov, who is a graduate student here at UNH, where on the top right you can see the density of a neutron star merger, a horizontal slice through the merger, and on the left you can see the magnetic energy density. Now I want you to pay attention to what's happening in the shear region between the 2 neutron stars, where you are going to rapidly grow small-scale instabilities due to the Kelvin-Helmholtz instability. And in that region, you grow small-scale turbulence, and you actually rapidly grow the strength of the magnetic field. So the problem here is that the smaller the eddies in these turbulence, the faster the instabilities grow. But we have finite numerical resolution, and we are very far from being able to capture that entire scale in which we expect these instabilities to occur, down to the viscous scale. And so what happens at the moment, what we are left with in the evolution of these systems is 2 possible choices. Either we start a simulation with very large magnetic fields, and then we can get to saturate the magnetic field after merger, but the large-scale structure of the magnetic field that we have after merger remains very dependent on our initial conditions in the simulation. Or we can start with a lower magnetic field, which is not going to impact the large-scale structure of the field after merger, but then we do not actually capture the saturation within the time scale of the merger. And so one way or another, we cannot, in my opinion, at this point, reliably predict what the large-scale structure of the magnetic field is after merger. And that is the main determinant of that uncertainty in the factor of 2 or 3 in the mass of the merger outflows after merger. So that's an important problem at the moment. And this is only really going to be solved by next generation code that can capture smaller scale magnetic field instabilities. One thing that is possible right now already is to at least capture the effect of angular momentum transport and heating from that small scale turbulence, which is going to drive the 15% of outflows that basically all simulations get. And that can be done with subgrid models, for example, the ones developed by David Radice. That part can actually reliably be captured now in simulations, in my opinion. But the extra component coming from the large-scale structure of the magnetic field, that one remains an important source of uncertainty. Right. And the second source of uncertainty has less to do with how much mass is ejected, but more what its composition is. And that's because most simulations do not have sufficiently detailed neutrino transport. And there, I think we are actually closer to being able to solve this problem. The main problem with neutrino radiation transport is that it's a high dimensional problem. We have to evolve the distribution function of neutrinos, the function of position and momentum for each type of neutrinos. And these functions are very strongly coupled to the fluid through neutrino matter interactions. Most simulations, because of that problem, makes very strong approximation, either using a leakage scheme or a moment scheme, that effectively introduce unknown errors in your simulations. And very recently, at least 2 simulations have been performed with the Monte Carlo algorithm that actually allows us to capture neutrino transport in simulations. And those are the post-merger simulations performed by the Los Alamos group, John Miller and collaborators, and the merger simulations that we have started to do with SPEC, neutron-star merger. And so one thing that we can start doing with these simulations is to estimate how well our existing predictions for the composition of the outflows in neutron-star mergers are, and that's what was done in this simulation here. You can see vertical slices through a neutron-star merger remnant. The white lines show you density contours. So you have the center of the neutron star here and the accretion disk around. And on the left is the Monte Carlo simulations, which does make some approximation in the very dense region at the center of the neutron star, so that it remains amenable to numerical calculation with our current resources, but otherwise evolve the equations of radiation transport. And the two-moment formalism here, which is an analytical closure for the neutrino pressure and for the energy spectrum. And you can see that there are some pretty significant difference in the composition of the outflows at the level of maybe 0.05 to 0.1 change in the electron fraction YE, which is actually a fairly significant change if you think about the outcome of nucleosynthesis in these systems. So the moment scheme allows you to qualitatively predict what kind of outflows you will get and where the more neutron-rich or less neutron-rich outflows are going to be. But it's quite likely that if we want detailed predictions for the composition of the outflows, we will have to actually use these more advanced neutrino transport methods. Okay, but here at least we are I think closer to getting a solution to the problem, closer than for the magnetic field issue, because now we have quite a few codes that have developed Monte Carlo transport, and there are alternative methods that do not use Monte Carlo, but instead spectral expansions, for example, that are being developed and might in the long term, actually quite likely in the long term, to overperform what Monte Carlo can do, but are not at the moment quite as advanced in their development. So it's closer to achieving a solution. All right, and to end this talk, I would like to also emphasize that even after you have finished your merger simulation, there is still a lot of uncertainty in propagating the outflows, heating them through our process nucleosynthesis, and then doing photon transport in the outflows. So I'm going to show you one potential source of uncertainty, which comes from a recent paper that Siva Darba and Dan Kaysen published based on starting from the outcome of one of our black hole neutron star merger simulation. And what is shown here is the difference in the density of the outflows if you include some heating from our process nucleosynthesis as these outflows propagate out, and if you do not include any heating. And you can see that there is a pretty significant difference in the geometry of the outflow with and without heating. In particular, in the simulation with heating, the outflows become more spherically symmetric and more smoother generally. So that's an important difference that is going to actually result in changes in the luminosity of the kilonova. So this is shown here, where you can see the bolometric luminosity edge on and face on with and without our process heating. You can see that without heating, the main dependence in the orientation of the system is whether you are edge on or face on. If you are face on, you see a larger cross section of the outflows. And so you get a larger luminosity for the kilonova. If you are edge on, you see a smaller cross section and generally have lower luminosity. If you do include our process heating, which in many models currently used is not done when producing kilonovae, at least not in 3D, you actually get a much more symmetric outflow, and you end up decreasing the difference between the edge on and face on case. But instead, the main dependence in the orientation of the observer is between different edge-on observers. Specifically, if you are in the direction in which the outflows are moving, you get a higher luminosity through relativistic beaming. And if you are, if the outflows are moving away from you, you get much lower luminosity. And again, this is factors of 2 or 3 differences in luminosity between different orientation. So that shows us that even beyond the numerical simulations of the merger itself, you should also worry about actually the geometry of your outflows if you are trying to make inferences about the properties of the outflow from a kilonova. And you also should care about many other uncertainties that I didn't mention here, including on the nuclear physics happening in the outflows, the opacity of various elements produced during the art process, and so on. So this leads me to my summary and where we stand right now. In terms of the simulation, the in-spiral and merger phase is pretty well understood today. In particular, we can provide some simple cutoffs in parameter space when observing a kilonova. In black hole neutron star merger, mainly on the spin of the black hole and the size of neutron stars. On the neutron star merger case, we can determine whether the system rapidly collapsed or not. But then when we try to go to more detailed parameter estimation, we are still hitting some significant uncertainties in our current models. In particular, the fact that B fields are under-resolved in the merger simulations, which I think is the hardest problem to solve. The fact that neutrino matter interactions remain approximately modeled, which I think we are getting closer to doing properly. And all of the other errors in going from outflows to kilonovae, which I didn't talk much about here today, but that are also very important in modeling these systems that many other people here are more knowledgeable in than I am. So at this point, doing detailed parameter estimation from kilonova observations remain a very difficult exercise that we should do with a lot of caution. The only thing that I would really be confident that we can do is do a simple cut through parameter space for black hole neutron star mergers. I'm going to stop here and take any question that you might have.
Thank you, Francois. So we have a question from George. George, go ahead.
Okay, can you hear me?
Yes.
Yeah, thank you. Thanks a lot, Francois. This is great. Excellent talk. I learned an awful lot in this. So I have two questions, really. The first is kind of a nuclear physics weak interaction question. The second is a relativity question.
Okay.
So on this issue of this speaks, of course, to the R process possibilities, but to whether or not the neutrinos can get purchase on the ejected material and thereby change its YE, usually in the wrong direction, increasing it. So you are
kind of R process you want, but yes.
Yeah. So you're sensitive to the composition. In particular, you're sensitive to whether protons and neutrons are locked up in nuclei or not, or free nucleons. That's just raw weak interaction matrix element calculus. So you're sensitive to what the entropy is, and low entropy means that as this material comes apart, it starts out as nuclear matter, it comes apart, it's going to heat up by fission essentially. And so what do you wind up with? What is the entropy of the ejecta? If it's high, that's probably good. Compared
to supernovae, it's pretty low. The dynamic the tidal ejecta, especially in black hole neutron star merger, is very cold.
Yeah, I get that. So I don't, I'm not counting the tidal ejecta. I'm really, worried about what comes off of that accretion disk.
It's like in the 10 to 20 kb per nucleon.
And is it sensitive to heating, to the sources of heating? Is all of the heating mostly, just from the nuclear matter coming apart?
No, this is what we measure close to the merger. Sorry, this is what we measure close to the merger. At much later time, after the R process has occurred, honestly, I wouldn't know the numbers off the top of my head. Someone who actually does a nuclear reaction network might be able to give you more information on that.
Okay.
10 to 20 when it leaves the merger.
10 to 20 is basically the answer I was looking for. So that's plenty high enough to dissociate nuclei into free nucleons and alphas. That's great. But then my question is this: in sources of heating, so I could just guess that you're close to hydrostatic equilibrium, and so roughly the enthalpy per baryon is going to be roughly the gravitational potential, the metric deviation, which is going to be what, like 20%?
Do you mean on the surface of the neutron star, or?
Near it, yeah. Where the action is taking place, and you're really tearing the neutrons.
Yeah, it's going to be roughly that. Right? I mean, it's basically the compactness of the neutron star. So that's for a post-merger remnant, maybe 0.2, 0.25, something like that, I guess.
Yeah, so that's pretty darn deep in a potential well.
Yeah, and most of the post-merger outflows in this system are going to come from somewhere, here or somewhere along the disk, and those would be much farther out. Those would be more like a few percent, probably.
Excellent. Okay, and then that helps a lot. And then finally, just I'm swinging for the fences here. I know that we don't have any real data from LIGO on this, but just thinking about angular momentum in the hole. And in the orbit, the orbital angular momentum, whether the spins are aligned or anti-aligned, and whether the heating you get could be sensitive to the angular momentum in the hole. If the hole is a high angular momentum, then can you get things like Blanford-Sanyazic? Can you get the Penrose process kicking in some way to juice up the entropy and the outflow rate along the polar axis?
Yeah. So there have been a few post-merger simulations showing that the fraction of the disk is unbound, and the properties of the outflows, including the entropy of the outflow, is sensitive to the spin of the black hole. It turns out that for neutron star merger, there is very little variation in the spin of the black hole in the post-merger remnant. They're all like 0.7-ish. In black hole neutron star merger, there is a little bit more variation, but less than you would expect, because the very low spin black hole or the entire line spin don't disrupt the neutron star. And so the interesting one tend again to have relatively high final spins.
Interesting.
So kind of everything is in that 0.7, 0.8, at most 0.9 regime, unless you start with a really maximally spinning black hole.
Yeah, but 0.9 is pretty high.
Yeah. 0.9, but 0.9 you have to start with like 0.8.
Very good. Okay, thanks a lot, Francois. This is wonderful.
Okay, the next question is from Shashank. He asks, how important, in your opinion, are neutrino flavor oscillations?
So I am told that they could certainly matter, but honestly, I'm definitely not an expert on that topic. I think many people in this call are likely to be more able than me to answer that question, because we don't have oscillations in our simulations. We basically at this point, we haven't run a simulation which included interactions between different types of neutrinos of any kind. We are starting to include pair annihilation, but we are very far from doing anything including oscillations right now in the merger simulations themselves. So this is, all of the studies have been done in post-processing. I don't know if Gail is here or someone else from our group. But they would be answered even more than me to answer this question.
Well, one issue is just again how fast the outflow is. Yeah. So if the outflow is fast enough, it doesn't really even matter whether anything oscillates, right?
Yeah. So the ones at the time of merger are reasonably fast, 0.2, 0.3 C, something like that. But the later ones are more. Starts maybe at 10% of the speed of light and then dropping at a very late time to a few percent only. But I guess by that point, the neutrino luminosity is pretty low too. So you can probably get to 5 to 10% of the speed of light at the time where the neutrino luminosity is still high.
So it's probably going to be the lighter ones then that are most affected, if at all, by oscillations.
The lighter.
The lighter systems.
It's probably more than maybe more than neutron star mergers, which are going to be more affected by what happens during the early wind phase. Yeah, I would think that's probably true. Yeah, I would think so. Yeah.
Okay, so Sanjay has a question. Sanjay, go ahead.
Francois, thanks for a nice overview talk. Question I have may have been addressed, but I'm sorry if I missed it. If the neutron star is very compact in a neutron star black hole merger, there would be no matter ejection, as you mentioned. Right. And would that provide a lower limit on the neutron star radius if we were to observe electromagnetic emission from a neutron star black hole merger?
Yeah, I mean, at least, it will give you a cut through the three-dimensional parameter space of black hole spin, radius, and mass ratio. And then presumably you would combine that with